Yeah. Okay, good morning, everyone. My name is Pavel Hayek, and I'm here representing the Plan for All Association, and I will be the moderator of today's webinar. Today's webinar is one from the series of webinars regarding or related to Agrihub INSPIRE Hackathon 2022. And today we will be talking about two challenges, actually, very closely related to each other. The first one will be challenge number 8, how to use and improve the second version of open land use. Let's call it map/database/product. And the second challenge will be challenge number 7, which will be the example of how to use open land use database. And that's called OLU for Africa. I am here today with my colleagues, Michal Kepka and Dimitri Kojuk, who will be presenting these two challenges to you today. So that's all from me for now. Just the information for you. This webinar is being recorded and it will be available at the beginning of the next week on YouTube channel of Plan for All Association. So you can watch it later as well. So now it's time for me to give the floor to Michal Kepka, and he will be talking about the challenge number 8. The floor is yours, Michal. Thank you.
Thank you, Pavel. So I will start sharing my screen if it will be successful. And I hope so. Yes, it should be working. Okay, so thank you for introduction, Pavel. So my task is to present you, let's say, features and attributes of new OLU database. First of all, just brief introduction, then the most important features this new OLU version is providing, some overview of data model, overview of, let's say, main advantages opposite to previous version, and then our colleague Dimitri will present some examples for Czech use case and for African use case. So it will be shown on real use cases. So what is open land use about? We are designing and developing almost since 2013 a seamless, harmonized vector database that is mainly focused on land use, land cover, but not only to these two themes. And we are trying to integrate the most detailed geometry that is available for particular areas or particular area of interest. The advantage is that we are trying to integrate more thematic datasets that are available, not only these two basic, but integrate more of them like topographic characteristics, land value, parcel informations, and so on. So large variety of topics and not limited only to just few topics. Originally, this open land use was designed as an evolution of INSPIRE land use theme. So it's not something separate, but some evolution of this theme. As I said, we have started to develop this open land use already in 2013. And in 2019, we decided to start a new version on 2. So briefly, what about this open land use version 2? At this moment, we were thinking how to improve the original database because it was really focused on basic themes, and we find out that most of the projects and use cases that are using open land use for version 1 would like to extend the thematic content and variety of attributes that can be integrated. So the main advantage for open land use, or the main will of Open Land Use version 2 was really the flexible in integration of thematic attributes. We have defined some structure of reference geometries. So these thematic attributes are joined to these reference geometries, and these reference geometries are the most accurate, most detailed geometries of these areas. We would like really to variable attributes, not limited to any database structure, to any structure of attributes, really what we have find out, what we have found, or realize that it's necessary to extend. So just add these attributes to some geometries or to define a hierarchy of geometries. So that was the additional feature we would like to define, or we have defined some structure and hierarchy of geometries and datasets. So based mainly on, let's say, map scale and thematic importance. So some small scale maps are ground layers, and in hierarchy top and top, we are integrating medium and large scales data sets and maps. But in this hierarchy, there is a problem how to visualize most of the data sets in one area, and how to really present to users particular attributes or attribute sets that they would like to see or need to visualize. Then we have designed so-called spatial temporal thematic views. So it's combination of data sets with some geometries, with some attributes combination, and based on some theme. So really visualize just amount of data that user would like to see or would like to get. These views are mainly defined or designed based on use cases, based on user scenarios. So we are not producing a lot of views at the moment. We are just producing views based on, let's say, user needs or user requirement. That's important. That you can get the full set of Olu, but if you would like some additional view or additional amount of data, or just some subset of data, it's necessary to define this thematic view. We have designed data model, the full complex database model. So because it's not just raster or just few tables with geometry and attributes, but it's complex data model. And we need to address a lot of requirements defined by research project, defined by use cases in recent years. So we decided to completely redesign the original data model and integrate this or address this requirement for integration of data analysis and data visualization. So how to be able to cover all these requirements. One of the advantages of this data model is trying to minimize redundancies of data. So really minimize amount of complex data sets. We are storing the full life cycle of each feature. So starting from first appearance in one data set, and when we are integrating same data sets for every 5 year, every 6 year period, so every let's say annual version of this data set, so we can cover evolution of particular feature in different thematic and time-stamped data sets. We are integrating or joining attributes from different data sets together to one this reference geometry. So based on spatial location, so we are joining or accumulating these attributes to reference geometries. And we are trying to provide level of details data set. So if you would like to see the small area, so this large scale map, you will see the most accurate, most detailed geometry with all these attributes accumulated in this hierarchy. Or if you would like to see, let's say, large area for region or for some state, then you will get only the small scale map with accumulated attributes just from the hierarchy that is in lower level of the hierarchy. So not to visualize all these parcels or these cadastral parcels, but to see the whole area with small scale map level. So data model in brief in UML diagram. So basics object are OLU object, so geometrical feature, and OLU attribute set, so set of attributes. This is one of the advantages of this data model. So we are dividing geometry and attributes because we would like to accumulate these thematic attributes to different geometries. So that's the reason why these two objects are divided. So there is many to many relation because of these spatial based joins. And how these attributes looks like when you just click on one feature. So this is attribute set of one feature. So you can see on top some ID of the geometry, ID of dataset where this geometry comes from, level of hierarchy where this geometry or where this feature is located in the hierarchy. So a higher number means a higher level of hierarchy, more detail level. And then there is array of attributes. I just highlighted with green this dataset ID. So this means that this geometry, datasets 789, means that this geometry has originally this set of attributes. So dataset 789 dataset ID. So this is the original feature with geometry attributes. But because it's a higher level of hierarchy, so it means that it has some join attributes from previous or small scale dataset. This means that there is another set of attributes from datasets 125 and some attributes from datasets 324. So it means that you can see more attributes in one geometry. And that's all from this, let's say, brief introduction. What we would like to improve in next hackathon or in this hackathon is to really optimize accumulating of attributes and adding more thematic attributes from different data sources. So how to smoothly integrate data sets to existing hierarchy of reference geometries and to basic reference geometries. At this moment, I would like to put the floor on Dmitry, so you will see use cases and let's say situation in current pilot localities. So Dima, floor is yours.
Thank you very much, Michal, for the introduction. And well, I repeat what Pavel said. My name is Dmitry Kozhuk, and I work for Plan for All Association. I work on development of this OLU dataset, and today I would like to show you some practical showcases how we use this open land use dataset around the world. I will start with the Czech Republic with Rostenice farm. It's an innovative farm that is taking part in many of our projects, and they are extensively using different ideas of precision farming and not afraid to use new things and informational technologies. And after I speak about Rostenice farm, I will go to Africa, where we'll speak about the history and the current state of open land use for Africa dataset. And it's actually related to the hackathon, because within the hackathon we want to complete the current version of Open Land Use for Africa to cover the whole continent. And in the third part, I will show you the use cases from China, because there is the project Sea Soil now running, in which we collaborate with some pilot locations in China. So I will start to share presentation, and maybe I will turn off the camera to save the bandwidth. So the first use cases, as I said, I will show in Rostenice. It's so that you can imagine where this Rostenice farm is located. It's located in South Morava region. It's southeastern part of Czech Republic, and the farm is quite big. It's having about 800, 900 fields. Here you can see the location of the fields, and actually we collaborate with them long time, and for reference geometries in this location we have used the following datasets: Core Land Cover and Urban Atlas. Those are pan-European datasets that's available for the whole Europe, and they're not maybe so precise, and in this context they don't have a very great value. Then we have this LPIS, which is Land Parcel Identification System. It's the Czech national system of fields, contains agricultural fields. Then we have this cadastral data, RUAN parcels, which are containing these land lots. And internally, because we are having closer collaboration with this farm, we are using their internal LPIS that is more detailed than the state LPIS, but the vector data, it can't go out, so it's just used mostly privately for some certain tasks. And for thematic data sources, what we use is the various vegetational indexes, for example, EVI index, then different classifications from Sentinel imagery. This is useful internally for them. The EVI index is useful in the sense that it helps to estimate yield potential and to estimate the health of the vegetation. So this is something that we use for internal purposes, basically to divide the fields into the zones where basically, like, this is the concept of zone management, and with the help of this EVI index, we divide the field into management zones, and depending on the value of this index, the farmer then can decide how much minerals he adds in each of these management zones. And then this Sentinel two classifications, they are mostly used now for some experimentation. So with this classifications, we can, for example, decide which culture is growing on each field, and to delineate the areas where this culture is growing. Then also from thematic data that we accumulate to reference geometries, we have this soil grids data set. It's published by the Soil Reference International Center, and we select some attributes from it which relate to the soil quality. This is organic carbon stock, organic carbon density, total nitrogen, and the acidity of the soil. And this we use within Sea Soil project, because the project is focused on analyzing how different factors affect soil quality. So these attributes that show us the soil quality, and then we do some analysis. So, for example, how land use is affecting the soil quality and so on. And also we have from thematic data some derivatives from European Union digital elevation model, some topographic characteristics such as elevation, slope, azimuth, and topological wetness index, and those parameters are coming from EUXDAT project that we had before, and it was also oriented on precision farming and to calculating some data that I used for decision making in farming. So here, first I will show maybe within presentation just some screenshots of these maps, and when this part is finished, I will show you the real map compositions and some basically some web pages, some hubs where we store this map compositions, so that in future you can just, when you have time, just to look at them by yourself. So here is the land use in composition, and here we select the most precise geometries. Mostly what you see is coming from Czech cadastre, and in fact in Czech cadastre there is also the attributes from which land use can be derived. So here is how it looks. You see that it's very detailed, and land cover composition is also mostly in this locality coming from digital cadastre. You can see also that it's very detailed. And these are some compositions that we did for Sea Soil project. For example, here you can see the fields, and you can see the mean, the average value of organic carbon stocks in soil surface layer. So you can see the basically fields in red, which have a big value of these carbon stocks, and that are more that are having more yield than the fields in pale red. Then also there is composition with total nitrogen in the soil surface area, and here you also can see which fields are good in this and which fields are not so good. So and now let's move to Africa, and regarding to open land use for Africa, we started to work on it in 2018 during INSPIRE Hackathon, and the first version it also came in 2018. The motive to create this data set for Africa, it was that in Africa nothing such existed. For example, in Europe at that time existed Korean land cover, urban atlas, but in Africa nothing like this. So we just did research of available vector data sources, because at that time we worked just with vector data sources, and it didn't exist this model about which Michal was speaking before me. So it was just like plain table in database. So from available data sources that time, it was mostly AfriCover dataset, which was created by a power organization, and here you can see the detailization. It had a 30-meter resolution, and it was very outdated. The most data it came from the break of 90s and 2000. And here, for example, you can see big city in Kenya on the border with Uganda, and it just looks like one area. So it was a very low level of detail. And then also we used some national data sources, because in this hackathon there were some people from Africa who collaborated with us, and they give us tips to some web pages where we can find local data sets. But again, it was something that was like either outdated, or the links were not working. And the third data source that we used, it was OpenStreetMap, and from OpenStreetMap it was just selected some areas that had this attribute land use for them. It was also quite a few of these areas. So now in 2021, as we already had this new model, and we started because now we had also opportunity to integrate some raster data sources. So we did research what is available, and we found out that it is some global raster data from which land use and land cover could be derived, and then we also find out that we can basically download very many linear features from OpenStreetMap database, and then we can polygonize these features to get the reference geometries, and then we will accumulate the attributes about land cover from those rasters, and connect it with these features from OpenStreetMap that we get by polygonization of line work. So here is an example already. You remember I was showing from AfriCover the big city in Kenya. So basically here how it looks in OpenStreetMap. You can see already that these geometries are much more detailed. And then here is this thematic raster that we used at first. It was this climate change initiative land cover dataset, which had 20-meter resolution and was derived by different methods of artificial intelligence from sentinel imagery. You can see already that it's quite detailed, and it's from year 2016. And then here what we get when we basically combined these reference geometries with the land cover. So we for each area, for each reference geometry, we calculated as the most popular value of land cover, and we in this way we interconnected it. So here how it looks, we can see that it's already very detailed, and we thought that it's a success. So we decided to extend this approach and to calculate the whole Africa using it. So it was calculated for the whole continent, and because it's difficult, it's millions of features, so it's difficult to render the whole Africa. So here I show you the rendering of some area near Lake Victoria. So you can see that it's incomparable level of detail with what it was in the first version. And then also for experimentation purposes, we used some data about multi-temporal unsupervised classification. It's basically some unsupervised classifications that creates, let's say, 20 classes. A person can choose how many classes he wants in these algorithms. And here, for example, it was 20 classes. And we can see that there is big correlation of certain classes with land use. For example, the blue class, it has very big correlation with build-up area. So the most dense areas in the city with the higher density, probably some residential areas, they belong to, they're like correlating with this blue class a lot. So this is additional information that was added for those parts where we had this imagery. It's basically border region between Kenya and Uganda. And here's the pie charts. They show exact distribution of each of these 20 classes within all of feature. Currently, we find out is that in 2021 in autumn, the ESA published even more detailed land cover dataset. It's called Volta cover, and it has 10-meter resolution. It's from year 2021, and we decided that we will use it to improve land cover categories, thematic data, but both that we will try to vectorize the features from this database to also improve reference geometries, because if you look at OpenStreetMap, you can see that in some areas, for example, in remote areas where no people live, it's not very precise, and this raster data can help a lot to improve the level of details of this reference geometries. So we created some function that downloads the data from the API of ESA, and then we tried to create, to incorporate this into open land use, for example, in Senegal and Gambia. And you can see that the level of detail even more precise than it was before. Here, how it looked just using reference geometries from OpenStreetMap database, and here how it looks now, where we incorporate this ESA World cover data. But of course, it's also very challenging, because this is very big raster data, and it's challenging to vectorize it and to work with it. The first challenge is the vectorization and to make this lines look smooth, and second challenge is that it's a very big amount of data, and you need to really create some basically processing in steps, or like parallel processing, so that you can process it in some normal time. So this what is actually, I'm coming to the aim of this hackathon, of these challenges that we would like to basically correct a little bit this vectorization algorithm, and then to run as a generation for the whole Africa. So this is also some example of Kenya-Uganda border region, and here also you can see that this is more detailed data also coming from this ESA World cover, and of course it's much more detailed than it was in the previous version. And also it helps a lot even if you integrate into it the thematic data from this unsupervised classification that I was speaking about, so that it even makes it more detailed if you use these additional techniques. But of course, now it's more like some theory. I think that we need some more motivation to have some more like practical use cases where people give us maybe some concrete aims where they can use this data. And of course, if you know some concrete aim for which you need to do this data, use this data, you have like more motivation to work on this incorporation and of this unsupervised classification into the results. So this maybe can be some task for future hackathons. Now we come to China. In China, also it's a similar situation as in Africa. There is not so many public data sources available. So here we have let's say 4 pilot locations within this sea soil pilot. It's some agricultural areas in China, and we do some analysis of the interconnection between land cover in these pilot areas with different soil parameters. So we want to estimate how the soil quality varies depending on some precise type of land use. So we again we created because in China it's a similar situation as in Africa, as I said. So to create reference geometries, we used mostly the data from OpenStreetMap, and then we added these thematical attributes from this soil grids data set. So it's quite similar as I was showing in Rostenitsa farm. Here is some concrete compositions, like this special temporal view that shows, for example, soil acidity in vicinity of Jiangsu pilot. Then here is, for example, the north west of China is showing organic carbon stocks in vicinity of this project. You can see that we know already the land cover, which was derived from this ESA dataset, about which I was speaking. So using this information about land cover, we can filter out the areas used in agriculture, and we can just calculate these parameters for areas that is used in agriculture. So here is organic carbon stocks in vicinity of this Changqing pilot. Here is organic carbon stock and surface soil layer in vicinity of Heilongjiang pilot, and here we have this sports pilot in China is Hebei pilot, and here is basically the average values of total nitrogen in vicinity of this pilot. So maybe now I can show some web pages where you can look through this exported special temporal views, and maybe because all these hubs that I will show, they have some data sources that are published there. So even if it's of your interest, you can create some web composition on your own. See. Do you see the screen?
Yes,
yes, you share your screen, we can see it.
Okay. So here basically this hub for everybody, where everybody can register and create maps. So if you go to map composition tab, you can see this list of compositions, and usually if it's some map composition that is using OLU, you can search it by typing OLU in this search field. So you open this composition, and you can see the clicked on different tab. Open. Then basically after this you need to close the map composition tab, and you can, for example, open other tab of selecting features, and then if you click on some feature, you can see the exact thematic attribute of this feature. So for example, here we have this land use special temporal view, and you click on the feature and you see its ID, and also the Hilux category of land use in which this feature is. So then also it's this seal soil hub, and on seal soil hub it works similarly. Here you can see the list of compositions, and here is the first 4 compositions. They're about various soil parameters that will calculate for the agricultural areas in vicinity of seal soil pilots. So for example, we can open soil acidity composition, and then let's maybe go to some Chinese pilot. Let's say here it's the vicinity of Aral city, and if you zoom in, you can see this areas that is used in agriculture, and if you click on if you click on some feature, then you can see the whole data from soil grids database that is connected to this feature. So here you can see at first the most important what we use for filtering out the features is land land cover type. It's certainly currently by this ESA classification system, and 40 is agricultural area. And then here you can see the list of all attributes from soil-based database, which is the nitrogen content in the depth of 0 to 5 centimeters and the mean value, and so you can see different parameters and different soil depths and the value of it. And, if you want to see exact legend of this map composition, you press on this button, and here you can see the values of different map classes. Now maybe the most interesting, if we look at the data for Africa. So here is the Senegal and Gambia area, and this is the previous version of OLU for this area, and you can see the level of detail. And now I will show you the current state, where you can see that it's already you can see even like small parts of the river, the small parts of the swamp, and in cities you can see very detailed different building blocks and so on. It has, of course, it has sometimes the problem this vectorization algorithm, for example. Concurrently, we're working on because sometimes this algorithm that I'm using, it leaves some stripes that probably make sense to connect with a bigger area around which this stripe goes. So this is something that will be solved during this hackathon. But I think that this is already quite a big achievement. Again, if you want to see this data about which I was speaking, that is derived from unsupervised classification from Sentinel, then you need to go this composition all of Africa and Sentinel supervised classification at vicinity of Busia city. This is the city at the border between Kenya and Uganda. So let's open it. And here already prepared these classes from here. It was actually unsupervised classification with 40 categories, and you can see that this blue, it really relates well with the density of built-up areas in the city. And additionally, here you can see the previous version of OLU. You can see this reference geometries that were created by using the data from OpenStreetMap, and you can see the previous version and basically the version that is incorporating this data from ESA World cover. And here it's actually how it looked approximately when we created the first version. Here is the Africover. And so in Africover, you can see that it's really not enough detailed to use it in some serious analysis for some real purposes. So I thank you for your attention, and I welcome you to join our teams at Hackathon, and maybe if you have some questions, you can ask.
Yeah, thank you very much, guys, for your presentations. I found them very interesting, and thank you for presenting the contemporary state of the work and stating some future issues we would like to deal with. And now I think it's time for particular questions. If somebody has some question, please speak up, or you can write down your question into the chat. That's one of these two options. And if you don't have a question right now, you can give the question to us via our email addresses, which are available at the Plan for All web pages at the part of this Agrihub INSPIRE Hackathon 2022. When you click on challenge number 8 or 7, you can find the context for us or how to reach us there as well. So I don't see any questions, but greetings at the chat. So greetings from Pilsen as well. And if there is no more question, let me wrap up our webinar, today's webinar. And we saw today how to use and improve open land use database, its second version, in a theoretical way as a description of challenge number 8, and then practically how the open land use version 2 was used for Czech pilot site in Rostinice, for Africa, and for some pilot sites in China as well. So I would like to thank all of you participating today's webinar. And as I already told you, this webinar was recorded and it will be available on YouTube channel of Plan for All Association. So thank you very much for being here with us, and we are looking forward to cooperate not only during this Agrihub INSPIRE Hackathon, but also in the farther future as well. So if you like what you saw today, you can register yourself for the challenge number 8 or 7 of this hackathon, and we will be happy to work with you. Thank you very much and have a nice day.
Thank you.
Thank you. Have a nice day. Bye-bye.